Today we're going to be talking about applications of Taylor polynomials. So let's remind ourselves what Taylor polynomials are. So we have the T-series, which we learned about last week, which is this thing, the sum from k equals 0 to infinity, the kth order derivative at wherever the series is centered over k factorial x minus a to the k, right? And the Taylor polynomial is what happens when we take not the entire series, but just the first whatever number of terms, so that we have n plus 1 terms, it's not important, whatever number of terms, so that we have an nth order polynomial out of this, right? So this thing is the sum from k equals 0 up to n of this. We defined this last time, but let's recap it like this, right? So what does it look like? So the first term is just f of a, the next term is this, the next term is this, and so on, and the final term is this. So it's an n-degree polynomial, right? It's a polynomial of degree n. The highest order term is n. Yeah? Cool. All right. So we also learned that to say that a function actually has a Taylor series representation is exactly saying that this thing, this nth degree Taylor polynomial, does a better and better approximation to our function over whatever interval we have the Taylor series expansion for. So let us draw a picture. Suppose we have something like this. This is our interval, and we have some function doing something like this, okay? So we know something about approximating this function already from previous techniques, right? We know that we can approximate it in the crudest possible way by simply taking a constant function at this particular value, right? So if we take the constant function given by f equals a, then it's some kind of approximation. It's really not a very good one, but it's something, right? It's not nothing. Blue pen. And how could we do better? Well, we could take a linear function. If we took a linear function, then it definitely does better, right? Take a linear function like this. Then that, as you can see from the picture, is doing a better job of approximating, at least when we get close to the values x equals a. Yeah? And if we take a linear function, what's that? That's exactly taking a tangent line. And as we discussed last time, that is taking the first two terms of the Taylor expansion, right? So the tangent line is just the Taylor polynomial T1. Yeah? It's the Taylor polynomial of degree 1. Yeah? Thumbs up if you see what I mean. Okay. So note T1 is just the tangent line. Okay. But the tangent line, as you know, is good when we are very close to A, but not necessarily good otherwise. So the classic thing that we've used this for previously is to approximate something that we can't easily calculate at a particular value. So recall, we used the t-line to approximate the square root of 101, right? Because if we didn't have a computer, if we didn't have a calculator, then actually finding the square root of 101 would be quite a pain, right? That would be a very difficult thing to do. However, we could simply take the square root function, right, and then consider its tangent line at the value 100, yeah? And if we did this, then we have a nice function that is easy to work with and easy to calculate because it's just a linear function, yeah? And then to approximate 101, we just say, okay, well, at 101, we're very close to 100, so instead of finding the value of the square root of 101, we're just going to put in the value 101 into the tangent line. And that's something we can actually calculate rather easily, yeah? And then we saw how good an approximation this thing was to the thing we actually wanted to do. Do you people remember this? This was all the way back in Calc 1. Is this coming back? Yeah, thumbs up if so, thumbs down if not. So if you don't remember this, then please go back and take a look. This is very good motivation for what this section's about. Because what this section about is a better, more general way to approximate things where you're not restricted to just taking the tangent line, but you're allowed to take higher order polynomials to approximate. And the advantage of that is that, as you can see, when you take the tangent line, as in this case, it's pretty good when you're close to A, but as you go further out, it's less good, and over here it's no good at all, right? Yeah. So if you're in a situation where you don't, when you're not trying to approximate something very close to the tangent line where you can actually calculate it, but where you want an approximation to hold true over an interval of some definite size, yeah, then you have another way to approximate, and that's to add more terms to your Taylor polynomial, yeah, which in terms of pictures means not approximating by a straight line, but approximating with things that are allowed to bend, allowed to curve. So if we're allowed to add a quadratic to this picture, then we can do something better. Maybe it'll do something like this. Yeah, it's a little bit better. If we're allowed to add a cubic, then we can have it bend even better, more closely following the function. Something like this. And every time we're allowed to add another term to our Taylor polynomial, yeah, we can fit this graph better and better and better, as I hope you can just see from this picture. Yeah. So T1 is the first Taylor polynomial. That's just approximating with a line. T2 is approximating with a quadratic. That gives us more freedom to fit the curve. Yeah. T3 is approximating with a cubic, even more freedom. T4, quintic, and so on and so on. Yeah. Cool. So what this section is about is approximating functions over some definite interval that is given to us, and then finding how far away the approximation is to the actual function. Okay, that's what this section is about. And again, this is the culmination of this whole series of topics, starting from sequences, series, power series, Taylor series, and now this, right? So this isn't a trivial topic. This is something that is somewhat involved. However, if you are feeling okay with everything we've done so far, then if you've built a solid foundation of all the stuff we've been talking about, then this isn't hard either, okay? So let's get into it. We will learn to approximate functions with the T polynomials and find the error. Or maybe find the error, i.e. how close the approximation is. Okay, I'm going to raise the board and we'll do an example. Now, there are two methods by which we're going to be able to approximate how good the Taylor polynomial is to the actual function. One of these methods is to use the Taylor inequality, which is what we discussed last time, which is the reason we know that Taylor polynomials ultimately do tend towards the actual function, and therefore we have a Taylor series expansion of a function. Okay, that's the heavy machinery. That's the powerful tool that we could always use. Okay, and the second method is that sometimes it turns out that when we do a Taylor series expansion and we look at the Taylor polynomials, no matter what value of x we have, it's always going to be an alternating series. And when it's an alternating series, then approximating the error is rather easy by the alternating series approximation. Yeah. So, two methods. The first method always works, Taylor's inequality, but this is, in a sense, harder and more technical because we have to calculate this quantity m, which is the supremum of the nth plus 1th derivative over the interval, Taylor's inequality. Okay, and the second method, sometimes T-series will be alternating. For all x in the interval. And in that case, we can use alternating series error approximation. Or error theorem, which is an easier theorem. Okay, so we're going to do an example of both. So the first example is this one. Approximate the function f of x is the third root of x by a Taylor polynomial, T poly, of degree 2 at a equals 8. That's the first part. And the second part is how accurate is the approximation over the interval 7 to 9. Okay, that's our problem. Let's draw a picture. So what do we have? We have this function, which is the third root. So what does it look like? It looks something like this. Yeah? And we are going to approximate this by a second degree Taylor polynomial over this interval here. Yeah? And then we're going to see how close this Taylor polynomial we use to approximate is going to be to the actual function. Yeah? And I'm not going to tell you which method we're going to use. We're just going to go into it, and then you tell me which method we can use. All right, so solution. First part A. So we need to find the Taylor polynomial of degree 2 at 8. This should not be too hard, right? So first, let's write down what the Taylor polynomial of degree 2 at 8 is in general, right? So T2 of x will be the function at the value 8 plus the derivative x minus 8 plus the second derivative over 2 x minus 8 squared. Yep. because it's just the first three terms of the Taylor series, because that gives us a polynomial of degree 2. And if we go any further, it's degree 3. It's not what we want. Yeah? Everybody clear on why this is the thing we want? Okay, everybody seems to be happy. Good. So this is what we need to do, and then we just need to calculate these coefficients, and then we'll have this explicit thing, right? So this is our function. F of x is the third root of this thing, which is x to the 1 over 3, and that's differentiated. We have 1 over 3, x to the minus 2 over 3. Let's differentiate again. We have 1 over 3 minus 2 over 3 x to the minus 5 over 3. And let's differentiate. So that's all we need, but let's differentiate it a third time because we're going to have to look at the structure, whether or not it's alternating, and if it's not alternating, we're going to need to calculate the third derivative to use Taylor's inequality. So we're going to take the third derivative as well. And then we're going to have 1 over 3 minus 2 over 3 minus 5 over 3, then x to the minus 7 over 3. And then let's put in the numbers. So f of 8 is the third root of 8, which is 2. F prime of 8 is 1 over 3. And then this is x to the minus 2 over 3. So x to the third, we've learned is 2. So we're going to have x to the 2 to the power minus 2. Yeah? So that's going to be just 1 over 4, this thing here. Are you happy with that? Yeah? Thumbs up if yes, thumbs down if no. Yeah, cool. Good. Then second derivative. So let's multiply this. We have minus 2 over 9. And again, we're going to first consider this as x to the third and then to the power minus 5. So x to the third is 2, and then to the power minus 5, we'll have 1 over 2 to the 5. And we can simplify that by cancelling the 2's. So we're going to have minus 1 over 9 times 2 to the 4. 2 to the 4 is 4 squared, which is 16, so it's 9 times 16, which is minus 144, I think. All right, so, and this guy, the third derivative at 8, so we're going to have 10, and then we have 3 so it's going to be 27 on the bottom here, and then we're going to have 2 to the 7, 1 over 2 to the 7, and, well, we don't need the exact value because we are just using this. Well, actually, let's just keep it like this. Let's just keep, yep. So that makes this 2 to the 8. Thank you. Cool. All right, so let's try and determine whether or not this thing is going to be alternating. Well, what's the sign of this thing? So it's positive, positive, then it's negative, then it's positive, right? So from 1 onwards, it goes positive, negative, positive. And if you look at this thing here, what keeps happening as we keep differentiating, we keep having these minus powers coming down here, right? So the sign of this thing, the sign of the stuff in front of the x, will keep alternating between positive and negative, positive and negative. Yeah? Yeah? So whatever number we put in here, right, we put in some positive number, whatever positive number we put in here, the sign of these coefficients will be positive, negative, positive, negative, positive, negative. Yeah? So the general expansion, right? So the T series, spell that right. T series is the sum from k equals 0 to infinity of the kth derivative at 8 over k factorial x minus 8 to the power k. And what we notice is that this part right here is flipping from positive, negative from 1 onwards. Yeah? So if we had x which was bigger than 8, that would be good because that gives us an alternating series. But if we have x that is less than 8, then this thing too inside here is also flipping between positive, negative. Yeah? So if x is less than 8, then this thing is not going to be an alternating series. Right? So in this region here, this thing fails to be an alternating series, and we can't approximate this part by the alternating series error estimation. So look at this. So sine of this expression is going to be, what's it going to be? So it's positive for 1, and then it's negative for 2, and then it's positive, and then it's going to be negative. So it's going to be minus 1 to the k plus 1. That's going to be the sign of this part here. Yeah? And what about this thing? And the sign of this thing will be if x is actually less than 8, it's going to be minus 1 to the k. So when we multiply these things together, yeah, it's going to be negative for every single term, k equals 1, 2, 3, 4, whatever, so long as x is between 7 and 8. So it's not going to be alternating. Do you see what I mean? Thumbs up if yes, thumbs down if no. Cool. It's something you have to look at a little bit carefully. It's not something that just jumps out at you. But if you do look at it, just step by step, the sign of this overall expression, right? Once we've picked an x, this is just a series. So the sign of this overall expression is the sign of this part and the sign of this part. And the sign of this part we can just see because it has this positive, negative structure we see happening as we keep differentiating. And the sign of this part is easier, right? If what's inside this bracket is negative, then it's just positive, negative, it's minus 1 to the k. Yeah? Cool. So not alternating. Yeah? So not alternating, and we can't use the alternating series error approximation theorem, right? We're going to have to use the full power of Taylor's inequality to actually answer this question about how good is the approximation over 7 to 9. Yeah? Yeah? Cool. All right, but since we have these things already written out for us, let us at least complete part A and write down explicitly what the Taylor polynomial is. Yeah? Taylor polynomial degree 2 is. So let me erase some space here. This might be something you have to watch more than once to have this fully sink in, because as I said, this is the culmination of all this stuff we've been learning for quite a while. And it's not the easiest thing to grasp straight away. So, T2, we have the thing here, right? We just need to put in the numbers. So f of 8, we know it's 2. F prime of 8, we know it's 12, or 1 over 12. X minus 8. And then this thing, it's minus 144. Thank you. So after saying the first part is easy, I actually do it wrong. Yeah, thank you. Yes. 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 Okay. Everybody with me? Yeah. Okay, so now I have to do part B. We're going to have to find how good this approximation is over this thing, and we're going to have to use Taylor's inequality. So we're going to need this expression over here. I need this expression over here. Okay, let's put down the expression we found for the third derivative. So we had that. The derivative at x was 10 over 27 x to the minus 8 over 3. Yeah. Cool. So, Taylor's inequality. Tells us the following, that if we consider the actual function f of x minus the second Taylor polynomial, then the difference between this and the function itself is m, and then it's going to be x minus 8 to the 3, because it's the next term, right? It's the n plus 1 over 3 factorial, where m is equal to the maximum over the interval, which is 7 to 9, of this third derivative. Yeah, that's what Taylor's inequality tells us. Yeah, and this is the thing that is probably hardest for you. That this looks like a difficult and complicated expression, and I understand why. It certainly does look like way. So in general, it's this, right? Well, that's the general expression. But I tried to motivate this by asking you to think about this as something analogous to the error estimation theorem for alternating series. And we know well that for alternating series, the difference between the nth partial sum, right, and the actual answer is the size of the n plus 1 step size. Huh? This is in a way analogous to the nth plus 1 step size, but it's a bigger expression. So the nth plus 1 step size isn't quite good enough. So instead of just having this, if this thing was just the nth plus 1 derivative evaluated a, then it would just be the nth plus 1 step size, but we have to make it a little bit bigger by allowing this nth plus 1 derivative to take its maximum over the interval we're interested in. You know? So if you feel a certain kind of resistance to this topic, probably it's because this expression seems complicated and it just comes out of nowhere, and I sympathize. But you can feel comfortable with this if you think about this as analogous to n plus 1, as analogous to the alternating series error estimation. And I can't do more than tell you that at this stage. If you learn more maths, as I hope you all do, you'll see why this is a natural thing. This has pictures explaining it exactly as all the other things I've explained it has. It's just too many too many pictures that I can't give it in this class. Okay, so we're just going to have to accept this as a black box tool that we believe we use. And that is the application of it to this particular case, right? So n is 2 in this case. So this thing is exactly this thing. Yeah? All right, everybody happy? Or somewhat happy? How are we for time? Yeah? Okay, cool. So we have to use this thing, yeah? And then it's just a matter of calculating what m is, right? And m is the maximum of the third derivative over this interval, yeah? Where are we going to achieve the maximum given that we know that this is the expression? Where are we going to achieve it? What's this function look like? Show me with your finger what this function looks like. Start with x0 and no, start with x1 and then x going towards infinity. What does it look like? Move your finger to indicate how it looks. Okay. So let's take a look. So this thing equals 10 over 27 x to the 8 over 3, right? Yeah. So if we start with 1 and increase x, as we increase x, the thing on the bottom increases, right? Yeah? So this thing is steadily decreasing from 1 onwards. See what I mean? Yeah? And what do we want it? We want to estimate the maximum of this thing over the range 7 to 8. So where are we going to find the maximum of this thing? That's 7, yeah? That's 7. It's a fairly easy structure, this thing. And anytime you need to apply Taylor's inequality, you will not have a difficult function to find the maximum over. It'll be something like this, like an increasing or decreasing function where it's really easy to see where this m is found. So m, in this case, is the absolute value of the third derivative at the value 7, right? So that is equal to 10 over 27 times 1 over 7 to the 8 over 3. And then that is some complicated number, which is pre-calculated and turns out to be 0.0021, or it's less than this. So the first 4 terms of the decimal expansion is this. Okay. So our function minus the secondary Taylor polynomial is less than equal to this number, 0.0021. And then what about this thing? What about this thing? Well, the maximum this thing is going to be is this is 9. 8 is right here. The maximum this thing is going to be in absolute value, this should be absolute value, will be when either x is equal to 7 or x is equal to 9. Right? When x is equal to 7 or x is equal to 9. Yeah? So this thing will be maximized by just 1. So this thing here, we just put 1. And then this thing is just 3 factorial, so it's just 6. Right? So this is 0.0021 divided by 6, which is a very small number, and it is less than 0.0004. Okay. So we got through it. Let's see what it says. What it says is that if we have this weird function, weirdish function, the third root of x, which does something like this, and we take the second degree Taylor polynomial, which is approximating it by quadratics. So it's going to be some kind of quadratic that curves down, right? Then, over this fairly wide interval of length 2, we actually have an incredibly good approximation. It is accurate to within 0.0004, right? So the gap between the quadratic and the actual function is less than 0.004. Yeah? So this actually does do a very good job of approximating your function. Okay? This actually does do a very good job. Okay, so we're almost out of time. I'll recap the steps and I'll do another example for those who want to see it. What did we do? We first had to find the Taylor polynomial, right? So we calculated the coefficients. Yeah? We calculated the coefficients of the kth order derivative of our function. Yeah? And then simply plugging in the coefficients gave us the Taylor polynomial degree 2. Yeah? But also looking at the coefficients, we saw that the Taylor series itself didn't form an alternating series. Yeah? Did not form an alternating series. So we have to use Taylor's inequality. Right? This is Taylor's inequality right here. Yeah? And it's a black box we can just plug things in. We can just plug things into this thing. Yeah? So we have this for our case when n is equal to 2, so therefore we have 3 factorial. M is the maximum over this interval of the third derivative. We know what the third derivative is. We have an explicit expression for it. We take the absolute value. We see that the third derivative is decreasing. So its maximum value occurs when x is equal to 7. So we plug in 7 into this thing. Plug in 7. Right? So that gives us what the m is, or at least bounds above what the m is, right? So this thing is bigger than our m, so put this in here. This thing here, over 7 to 9, its maximum value is 1, yeah? And this is just 6, so it's this thing divided by 6, which is this thing, yeah? So this is true for all x between 7 and 9, like this. And this is of real use because not that long ago, we did not have the ability to find things like what the third root of x was, right? And that was a very hard thing to calculate, yeah? And if you were someone building something that required you to know what the third root of x was for any number between 7 and 9, right? Then you could either just work very hard with some algorithm to calculate each individual value between 7 and 9, right? Or you say, okay, I'm building something and it has some error tolerance and it's probably not going to break apart or fall down if I'm within 4 decimal places of the accurate answer, or 3 decimal places, right? So I'm not going to deal with the difficult thing of calculating the third root of x over this interval. I'm going to take the second degree Taylor polynomial and see how close it is. And if you did that, then you just have something that is reasonably easy to calculate, right? You can, without too much difficulty, make calculations with the second degree Taylor polynomial, which again was this thing. This thing is a nice function. This thing is not hard to calculate. If you take your value of x between 7 and 9, you can calculate this reasonably quickly, whatever it is. Yeah? Whereas if you're trying to by hand calculate the third root of x for an arbitrary value between 7 and 9, that's really difficult. Yeah? So this is how your grandparents, great-grandparents, built the world. They approximated difficult functions that came up as part of their process of constructing things by Taylor polynomials. Yeah? And maybe this guy wouldn't be good enough. Maybe the error tolerance of 0.004 isn't accurate enough and they want something better. Then they would take a higher degree polynomial, they'd take a next power, they'd approximate it by a cubic and have an even smaller error. Yeah? Yeah? So this is done a lot in physics, that you have some function that comes up and it's a difficult function and you don't understand what it is. So you say, okay, well, I think it's good enough to take the second, third, whatever, fourth Taylor polynomial that approximates it and just work with that, because then that's an easy function. It's just a polynomial. And it's also done in maths quite a bit. I do this too. So this is a generically useful technique. You replace the difficult thing you're trying to understand with a simple thing, a polynomial. And it turns out you can do that and have something that is very, very accurate over your interval. And you can see how close the accuracy is with this powerful tool, Taylor's inequality. Okay? Cool. All right, that's just one example. We have another example, but the next example will be easier because we're now going to do the case when we have an alternating series. And that's what's coming up next. So leave it anytime you want, of course. And please watch the video for the other example of how to actually do this. What is the max possible error in the approximation for 0.3, which is less than equal to x, which is less than 0. Oops, minus 0.3, which is less than 0.3. And b for what values of x is this approx accurate within zero point 0.005. Okay, so solution. So let's see what the question is asking us. So what's the maximum possible error in this approximation? Okay, so sine is approximately equal to this. This is the 5th degree Taylor polynomial. This is a polynomial degree 5, right? Yeah. And it's asking us how close the 5th degree Taylor polynomial is to the actual Taylor series, to the actual function which is given by its Taylor series. Yeah? So, over this particular interval. So, note the t series of sine, we did this on Friday, is this. It's the sum from k equals 0 to infinity of minus 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial, right? This is what we learned. Yeah? And it's asking us to approximate this over this interval from minus 0.3 to 0.3. Let's draw a little picture. So this is 0, this is 0.3, this is minus 0.3, and we have a sine function. So sine function, so it looks like this. Okay. And we have the 5th order Taylor polynomial, which is some function like this. Say, I don't really know exactly what it looks like, of course, but this represents it. So this is T5. And this thing here is sine. Okay. So it's asking us what's the gap between this polynomial and this function. Yeah? Now, if we look at this thing right here, note that if x is positive, then this expression right here is positive, right? Yeah. So if x is between 0 and 0.3, this is a positive expression right here. Yeah. And therefore, our series is an alternating series. Yeah. Our series is an alternating series. Everybody with me? Cool. Now, if x is negative, then this is a negative number for every single k. If x is negative, then this is a negative number because we're taking x to an odd power. So for any x between minus 0.3 and 0, this is going to be negative for every single k. So it's not changing sign. As k goes from 0 to infinity, this thing is either positive forever or it's negative forever. It's not changing sign. Yeah? Thumbs up if you're with me. Cool. All right, whereas this part in front here definitely is changing sign. Yeah? So what this means is that this entire thing is an alternating series. No matter what x we choose, in this interval here, this is an alternating series. Yeah? This is an alternating series. Previously we had that the power of x and the coefficient cancelled signs when we had x between 7 and 8. Yeah? So then it wasn't alternating. This case, no matter what x is, this guy will be alternating no matter what. Yeah? Which makes life very convenient for us. Yeah? Note that no matter what x is, unless x is 0, which is trivial, so note that for any x not equal to 0, the series sum k equals 0 to infinity minus 1 to the 2k plus 1 x to the 2k plus 1 over 2k plus 1 factorial is alternating. Which is good news. Okay, so once you pick your x, when you look at the series, it's an alternating series. Yeah? So, can apply the alternating series error approximation. So, we want to find out how close this thing is to its 5th degree Taylor polynomial. Yeah? It's 5th degree Taylor polynomial. Yeah? And if we write out the first terms of this thing, right? So, sine of x is equal to x minus x to the 3 over 3 factorial plus x to the 5 over 5 factorial. And the next term will be minus x to the 7 over 7 factorial, right? So again, think of x as being fixed. We've chosen x, some x between minus 0.3 and positive 0.3. Yeah? And then the first three terms are these guys, right? And we want to find the difference between these first 3 terms and the actual series. And it's an alternating series, right? So we are going forward, and then backward, and then forward, yeah? In our first 3 terms. And then everything we do after this is the error. So the actual answer, right, is whatever. It's something between here, and its size is less than the nth plus 1 step size, right? And the nth plus 1 step size in this case is this thing. Yeah? It's this thing. Yeah? Cool. Now there's a possibility for confusion here because this is 7, right? The power here is 7, but it is the 4th term in the alternating series. So you have to distinguish, once you've chosen the x, the power of the x and the number of terms that we're dealing with. They are not the same, right? They are not the same. Because the power of x is taken to this 2k plus 1, so this is definitely not the same as the number of terms. So that's a possible point of confusion. Yeah? But don't get confused, and it's not hard to not get confused once you pick the x and just think about this as an alternating series, right? This is an alternating series, this is the nth plus 1 term, yeah? So then we have other things here, but we don't care because we just want the nth plus 1 term, so plus blah, 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 blah. So, by alt series error theorem, we have that sine of x minus these terms, these first 3 terms, is less than the absolute value of the nth plus 1 step size, in this case, the 4th step size, which is this thing, so the absolute value of x to the power 7 over 7 factorial. Yeah, that's all we need. That's all we're using to say this. And this is true. This is true. Yeah, for any pre-chosen choice of x. Yeah. But what we want is to know how close this is for any x inside this thing. Yeah. Yeah. So this is true no matter what x you have, right? But we want to know how close it is for any x inside this range. Yeah. Which means knowing how big this can possibly be for any x inside this range. Yeah? So what value of x inside this range is going to make this thing as big as possible? .3 or minus 0.3, right? Because we're taking the absolute value. Yeah. So this thing, well, let's leave this. This thing is less than 0.3 to the power 7 over 7 factorial for any x between minus 0.3 and 0.3, right? So this is true for any x between minus 0.3 and 0.3. So this part right here is true for any single pre-chosen x. But this part is true for x within this region, right? So the overall thing we want to know, which is how close sine is to this thing over this range, this is the answer. Huh? This is the answer. And this thing is some number that, again, we can just calculate. So this number, as you might guess, is a very small number. This is like 4.3 times 10 to the minus 5. We have an incredibly good approximation with the 5th degree Taylor polynomial of our sine over this fairly short interval. No surprise, huh? Cool. All right, so that's part A. That's part A. I'm going to erase the board, and then we're going to do part B. Think about how we do part B. So part B is for what values of x is this approximation to within this thing? Okay, think about that. Okay, what did we learn? We learned that sine of x minus this thing here, the 5th degree Taylor polynomial, is less than absolute value of x to the power 7 over 7 factorial for any pre-chosen x. Yeah, that's what we know. And what are we asked? We are asked what values of x allow us to approximate sine with this 5th degree Taylor polynomial to within this small error of 0.00005. So want error less than 0.00005. Yeah? Okay. So, let's draw a picture. we have this fifth degree Taylor polynomial. And what does this information say? This says that if we inherit x, then the maximum distance between the polynomial and the function is less than this, right? And we want to find an interval for which the error is less than this thing, okay? So, tell me how to do it. Or set me in the right direction. Express what we want in terms of the information we have here. Yeah, so let's put these things together. So we want error less than this, and this is the error, right? This is the error. So this is the error. And we want error less than this. So we want mod x to the power 7 over 7 factorial to be less than 0.00005. That's what we want. And for all x's for which this is true, then our approximation is within the error that we are prescribed, right? And all we've done is rephrase the information and the question with the language of math, huh? So, as you say, in order to find what range of x is going to satisfy this, we could just set this equal to this, because as x increases, then this thing gets bigger, right? Yeah. So if we find the x for which this is an equality, that'll be the biggest possible x for which this still remains true, for which this error remains true. Yeah? Everybody see that? Yeah? Thumbs up, people with the icons. So, if we set mod x to the power 7 over 7 factorial to be equal to 0.0005, we find the biggest mod x for which we have error that we want. So, let's just unpack what that says. Oh, this is factorial. So that's the same as saying that mod x to the power 7 is equal to 7 factorial times 0.00005, and therefore mod x is the same as the 7th root of 7 factorial times 0.00005 to the 1 over 7. And this we can actually compute. This turns out to be 0.252 to the 7th root, which is less than, oh, it's actually equal to 0.821. So, that means for any x which is between minus 0.821 less than x less than 0.821, we have exactly the inequality that we want, right? Sine of x minus x to the 3 over 3 factorial plus x to the 5 over 5 factorial is indeed less than 0.00005. Yeah? Cool. So in essence, this isn't harder than finding an alternating series, finding a number of terms required to get an alternating series partial sum to within some particular error. Yeah? Because this is the error estimation from the alternating series, and all we need is to have that this quantity is less than this. That's what we wrote down, right? And this will be to find out what range this is true. Since this is increasing as x increases, we set x equal to this, and then for any x whose absolute value is less than whatever we solve this to be, it's definitely going to be true. Yeah? See what I mean? Okay, cool. So we set this equal to this, then it's just numbers, blah, blah, blah. We get this quantity here, we put it into a calculator, we get this thing. That's the number. And therefore, for any x inside this range, we have this small amount of error. Yeah? Cool. So you have to keep your wits about you somewhat with this. You have to think carefully what you're doing, and I strongly recommend you track what you're doing by drawing pictures all the time and seeing on the picture what you're actually trying to find. Do not find yourself learning a sequence of steps and performing them. Try and make sure you know what you're doing and what this stuff means, why it's working as it goes along. But if you are comfortable enough with the topics this is based on, series, alternating series, you won't struggle with this. You will ultimately feel confident with this. So you're going to have to practice this. This is one of the harder topics, but you will succeed with this. All right. Any final questions before we wrap up? Okay, cool. So now I have office hour. Stick around if you have questions. Otherwise, I will see you all on Wednesday. Bye-bye, everyone.